This is the lecture for Module 7 in the book Problem-Solving Guide for Electromagnetism and Optics, the subject of which is the magnetic force. The first semester of this course, we discussed gravitational force. Gravitational force acts on objects with mass. It's always attractive. There's only one type of mass. Electric force acts on particles with electric charge. There's two types of electric charge. Electric force can be either attractive or repulsive. The force is along the field lines if the charge is positive, and opposite the field lines if the charge is negative. Here we introduce the magnetic force. The magnetic force is quite different from both the electric force and the gravitational force. First of all, there's no such thing as a magnetic charge. Magnetic fields are produced by moving electric charges, and they act on moving electric charges. If a charge is sitting still in a magnetic field, it doesn't feel a force. It has to be moving. The convention for the direction of the magnetic field lines is from the North Pole to the South Pole, like this. Note that the field lines are complete loops. They have to be complete loops because there's no magnetic charges. Electric field lines start on positive charges and end on negative charges. There's no magnetic charges, so these must be complete loops. If you're a problem solver, you might be thinking, hey, wait a minute. What if I just break off the north part of this magnet? Won't that be a magnetic charge? And the answer is no. As soon as you break it, the bottom of it becomes a south pole. You can't isolate magnetic charge. There's no such thing as magnetic charge. In this module, we're only going to be focused on the force on a charged particle moving in a magnetic field, not what's producing the magnetic field. That's the next module. The magnetic force on a moving charged particle is Q V cross B. It's weird that the force depends on the speed. If the speed is 0, there's no magnetic force. B is the magnetic field. Q is the charge. The units of magnetic field, if we solve for B by putting Q in the bottom and V in the top, Q and V in the bottom, it's a Newton second per Coulomb meter, and we need a unit for that. So we called it the Tesla after the car. I'm just kidding. It's after Nikola Tesla. This cross is a vector cross product. It's not multiplication. This gives the direction of the force. The magnitude of the cross product, V cross B, is VB sine theta, where theta is the angle between V and B. So there's a few strange features of the magnetic force. As I discussed previously, a charged particle that is sitting there experiences no force. The faster it's moving, the greater the force. Second, it experiences no force if it's moving parallel to the field lines. If it's moving along the field lines, it experiences no magnetic force. If V and B are in the same direction or 180 degrees apart, sign of that is 0. Finally, the direction of the force is perpendicular to both the velocity and the direction of the field. Perpendicular to the field. The force isn't along the field, it's perpendicular to the field. So let's figure out the direction of the force from the field and the velocity. We're going to use the right-hand rule. And here's the convention. You point your thumb straight out. That's the direction of V. Point your fingers in the direction of the field, B, and your palm pushes in the direction of the force for a positive charge. That's supposed to be a positive charge there. So your palm, think about your palm pushing in that direction. The force is directly out of the page. If the particle had a negative charge, it would flip the force and it would be into the page. So the first step is getting V cross B and then determining the direction of the force based on the charge. The right-hand rule gives the direction only of the cross product, V cross B. The expression for the magnetic force, if you recall, is Q V cross B. So if Q is negative, it flips the direction of the cross product. Let's practice. So we have a negatively charged particle moving into a magnetic field that's directly out of the page. OH minus particle moving into this field. The B field lines are directly out of the page right at you. What's the direction of the magnetic force as soon as it enters the field? So we have to put our thumb along V. It's going to be hard to do if you're facing the screen. You got to put your right hand sort of behind you to get your thumb pointing to the right. And then you got to point your fingers in the direction of the field, which is directly out of the page. And if you do that, your palm should be facing down. Your fingers of your hand should be pointing directly away from the screen, and your thumb should be pointing to the right. Your palm should be facing straight down. Make sure you use your right hand. That's the direction of V cross B. But the charge is negative. The force is given by QV cross B, so the magnetic force is upward. As soon as this particle enters this field, it's going to be pushed upward. The particle is going to accelerate upward. It has an upward force. This will change the direction of the velocity. The direction of the magnetic force depends on the direction of the velocity, so the magnetic force is going to change as well, because the direction of the velocity is changing. The magnetic force is always perpendicular to the velocity. It's pushing perpendicular to the velocity, which means it can't possibly speed it up. It can't change the speed, it can only change the direction. It produces an acceleration, but it's a centripetal acceleration. So the particle moves in a circle. The faster the particle, the bigger the force. It's QVB. The bigger the force, the bigger the acceleration. The bigger the acceleration, the smaller the radius of the circle. So this particle, not moving that fast, circular arc. If you shoot it in a little bit faster, it's going to curve a little bit tighter. And shoot it in even faster than that, it's going to curve very quickly. This is a powerful technique for determining the molecular composition of a sample, because you can separate the particles by mass if you can shoot them in all at the same speed. If they enter at the same speed, the heavier one will curve less, and the lighter one will curve a lot. This is an instrument called a mass spectrometer. Mass spec. It separates the ions by their mass. So let's consider how we might get a bunch of randomly moving ions to move at the same speed, in the same direction, into the magnetic field region. We want to push them down the barrel of a gun. We can do that with an electric field, but how do we get them to be moving the same speed? And there's a very clever technique. We can use a velocity selector. If they're moving too fast, we filter them out. If they're moving too slow, we filter them out. And here's how we do that. We shoot in a bunch of ions at different speeds in the same direction. Only the ones that are going the right speed come out. If we have crossed electric and magnetic fields, we can do this because the magnetic force is a function of speed. So let's look down the barrel of the gun from this direction. Here we have an E field down and a B field to the left. If we shoot a particle down the barrel, what are the direction of the forces? The particle's going into the page, which means if you want to get the direction of V cross B, your thumb has to point into the page. The electric field is easy. If you thought the electric field is hard, just consider the magnetic field. It's a positive particle. Fe is QE. It's independent of the speed. Since the field is down, the charge is positive, the electric force is downward. Fe is downward. Now we have to get Fb. So we point our thumb down the barrel, into the page, and we put our fingers pointing to the left. If we do that, the palm is facing upward. That's the direction of V cross B. It's a positive charge, so the force, the magnetic force, is upward. This magnetic force will grow and shrink based on the speed of the particle. The electric force doesn't do anything, doesn't change with speed. If the particles are moving too fast, the magnetic force will be bigger than the electric force. So the particles will be the positive particles will be deflected upward and smash into the barrel of the gun. There's the magnetic force is too big. The particle's going too fast. If they're going too slow, the magnetic force is weak, and the electric force is going to win, and it's going to hit the bottom of the barrel. If it's just right, the electric force and the magnetic force will balance. One's up, one's down. The particle is going to go straight through and make it into the magnetic field region. A very clever idea to get all particles moving at the same speed. Once they're in there, heavy particles will curve less sharply, lighter particles will curve more sharply because they all enter with the same speed. To determine the speed that's selected for, we set the forces equal. So now we're going to do quantitative calculations. Fe equals Fb. Fb is QV cross B. V and B are at right angles. Sine of 90 is 1, so that's just QVB. And the electric force is always QE. The charge cancels out. This has two important consequences. If you have a velocity selector that works for positive charges, it works for negative charges as well. If the velocity works for singly ionized particles, it works for doubly ionized particles because the Q's cancel out. We now have V is E over B, VB is E, so V is E over B, and then we can calculate the speed that the velocity selector selects for. It's just E over B, independent of charge, independent of mass. If you want to select for ions moving at 80,000 meters per second, and we have an electric field of 10,000 newtons per coulomb, 10,000 volts per meter, we need a magnetic field of 125 millitesla. So now let's do a real-world problem involving a mass spectrograph. Carbon-14 is radioactive. It's got a half-life of 5,730 years. It's constantly being produced in the Earth's upper atmosphere. So there's this sort of equilibrium amount of carbon-14 in our body. It's about 1 part in a trillion. So living things have a natural concentration of carbon-14 because we are carbon-based. Plants take in carbon dioxide from the atmosphere, so they get carbon-14 from the atmosphere. Humans take in carbon by eating plants and animals. So there's this equilibrium of carbon-14 in our body. When a living thing dies, it stops exchanging carbon with the environment. So the carbon-14 gradually goes away. It's not taking in any more carbon-14. Carbon-14 is radioactive. Something's been dead for a long, long time, a fossilized tree or something. Carbon-14 in it, very small. That's how you date things, based on carbon dating. The lower the concentration of carbon-14 relative to carbon-12, the older the sample, in general. In 1981, glaciers are receding, global warming, hikers in the Alps walking along, and they discover a human body sticking out of the ice. What the heck? Here he is. Ötzi the Iceman. How old is Ötzi? Well, take a sample from the body, analyze it for carbon-14 with a mass spectrograph. Carbon-14 is heavier than carbon-12. Let's put some numbers in there. The magnetic field, 250 millitesla. The speed of the triply ionized carbon atoms is 2 million meters per second. The sample naturally contains carbon-12, carbon-13, and carbon-14. What's the separation distance of the carbon-12 and carbon-14 at the detector. So here's the instrument, and here's the detector. The carbon atoms are going to come in all at the same speed because of the velocity selector. The carbon-14 is going to take a big arc because it's heavier. Carbon-12 is going to take a smaller arc. And if you measure how much carbon-14 there is in the, relative to carbon-12, you can date UTC. So the velocity selector gets all the ions going at 2 million meters per second. In the magnetic field region, they all experience the same magnetic force, QV cross B. The acceleration it produces is v squared over r. It's perpendicular to the direction of the speed. Setting the force equal to ma, the force is QVB, that's ma, acceleration is v squared over r. We can get the radius of the arc, r. One of the v's cancel, we get mv over qb. Now we have to calculate the mass of those things. Carbon-12, 12 grams per mole. Converting to kilograms, getting one atom, an atom of carbon-14, 1.99 times 10 to the minus 26 kilograms. Carbon-14 has 2.33 times 10 to the minus 26 kilograms. It's heavier, of course. We can calculate the radius of the arc, 33 centimeters for carbon-12, 38.8 centimeters for carbon-14. Here's carbon-12, there's carbon-14. These are the radii. All right, so the separation distance, we have to use their diameters because they're going half an arc. So the separation distance is about 11 centimeters from here to here, which is pretty big for carbon-12, carbon-14. There's one more concept you have to cover in this module. It involves charges moving in the magnetic field, but these charges are in wires. Electrons moving through conductors, not ions moving through empty space. Electrons moving through conductors go very slow. The drift velocity, as we have seen in Module 5, is pretty small. So let's consider an aluminum bar that we put in an external magnetic field. That magnetic field is into the page, and the conventional current I is to the right. So here's the aluminum bar, a section of the bar. There's this external field that we're not considering where it came from. Now the electrons move in the opposite direction of the conventional current. So if the current is to the right, in reality, the electrons are drifting to the left. So there's the drift speed. These are charged particles moving in a magnetic field. So let's figure out V cross B. I have to point my thumb to the left in the direction of V. My fingers point into the page, and my palm is facing down. But electrons are negative. So when I do Q, V cross B, the force, the magnetic force on the electron is upward. As a result, the free electrons in the bar will shift upward. This is going to produce a negative charge up here and a positive charge on the bottom, like this. This is something like a capacitor, and it makes an electric field. It produces a vertical electric field when a current's moving in a wire. So the electric field is upward, the direction a positive charge would go. So there's the electric field, upward. An upward electric field produces a downward force on the electrons. Electrons are negative. Thus, a natural velocity selector is set up in the aluminum. The magnetic force pushes them upwards, but then when they go upwards, that produces an electric force downward. Those are the two forces. And the velocity that it selects for is the drift speed of the electrons, V sub d. It's very small compared with free ions moving through empty space in a mass spectrometer. Since the speed is small, the magnetic force is small, the electric force is small, the voltage difference between the top and the bar, bottom of the bar is small, something like 1/1000th of a volt. This voltage between the top and the bottom of a wire carrying a current in a magnetic field is called the Hall voltage. So let's do a problem. Aluminum bar is a square cross section, 1 centimeter by 1 centimeter. The height's 1 centimeter. The depth is 1 centimeter. It's carrying a current of 2 amps to the right. Electrons are drifting to the left. The external magnetic field is 100 millitesla into the page. What's the Hall voltage? The vertical Hall voltage. To get the magnetic force, we need the drift speed of the electrons, and to get the drift speed, we need the free electron density in aluminum. And we've done this before. Aluminum has a density of 2.7 grams per cc, an atomic weight of 27 grams per mole. Each aluminum atom contributes 1 electron to the current. There is the free electron density in aluminum, 6.02 times 10 to the 22nd electrons per cubic centimeter. We can calculate the drift speed. V drift is I over NAQ. 2 amps is the current. There's the electron density. That's the cross-sectional area of the wire. That's the charge on the electron. And we get 2.08 times 10 to the minus 4 centimeters per second. If we're going to use SI units, we need to get that to meters per second. So 2.08 times 10 to the minus 6 meters per second. The drift velocity is the speed at which the upward magnetic force balances the downward electric force. The magnetic force is a function of speed. So we have the magnetic force, Q V drift B equals QE. Cancel the Q's. The electric field is V drift times B. And we know 2 of these. There's the drift speed, and there's the magnetic field, given 100 millitesla, 0.1 Tesla. So there is the electric field between the top and the bottom of the bar. But we don't want the field, we want the voltage difference, the Hall voltage. 2.08 times 10 to the minus 7 volts every meter. But this is only 1 centimeter. If it drops 2.08 times 10 to the 7th in a meter, it drops 1/100th of this in a centimeter. The Hall voltage is 2.08 times 10 to the minus 9th volts, 2 billionths of a volt. Now it's your turn. Do some problems, lots of them.